Hello, guys. Apologies for putting this up so late. I was kind of busy this week. Anyway, we're finally in the new chapter, chapter 16. So in this chapter, we're going to be dealing with vector calculus. Basically, to some degree, it is an extension of the fundamental theorem of calculus. So that theorem states that in some way, taking differentiation and integration are inverse operators. And throughout this chapter 16, we will see different formats of that particular theorem with different types of differentiation and different types of integration. So the central object that we will be operating is this first topic, the vector fields. And then start off from 16.2, we will be introducing different objects of differentiation and integration, and then combining them together to get a different format of fundamental theorem of calculus. I will draw a map, I would presume in maybe 16.3, so that you can refer to in which theorem are you using in which domain. And then you can get a better understanding on the whole picture of the vector calculus in this chapter. Right, so let's start now. So this first section, 16.1, is quite naive. We're simply introducing this object called the vector field. And vector field is actually nothing but an assignment that assigns a point towards a vector. So although these two are all belong to R2, but you can regard this as a point and this as a vector. So for each point, you have a starting from that position, you have a particular vector that points towards some other points. And then by combining those vectors, you get a vector field. Obviously, we can extend everything what I mentioned here to R3. So you can obviously assign a point in the Cartesian 3D dimensional system to a 3D vector. Okay. So for instance, a very naive example, let's set f1. Notice that I put a vector arrow here. That means that this is a vector function. So f1 xy at the position x and y is given by xi plus yj, which is simply xy, right? So that is saying that the position xy will assign you the vector xy, the same as the position vector. So for example, we can draw that out. In this first example, we see that, for instance, this point 1, 1 is assigned to the vector field f1, 1, 1. So you have an outward pointing vector. And similarly, for 2, 2, you have the outward pointing vector f1, 2, 2 to be again 2, 2. So it is in the same direction, but longer than the point at 1, 1. So you can see that if we assign the point to the vectors and we draw it out on this Cartesian plane, then we see that it is a blowing outward vector, where if you go all the way along the vector, when a point is far away from the origin, then the vector field is stronger. So the strength of the vector field increases when the position is away from origin. Now, for the second vector field f2, xy, I define it by y minus x, or you can write it as yi minus xj. Both of these notations are useful, so make sure you understand both of them. So I assign y minus x. For instance, if you're dealing with the point 0, 1, then by the formula, you see that the corresponding vector is 1, 0. And if you're dealing with 1, 0, then the corresponding vector will be 0 minus 1. So actually, you can see that since the dot product between this guy and a positional vector is always 0, so we see that the vector field is always tangent to, actually always orthogonal to the position vector, like this, or like this. Okay, so it is sort of a circling vector field if you draw it out. Now for 3D space, let me use a very naive example. I assign xyz to the zk vector field, which is 0, 0, z. So basically, it is symmetry with respect to the x and y coordinate, but for different z, you are assigning different vectors. At the same plane, which you have the same height, each vector are of the same strength. And when you are far away from the origin, actually the xy plane, then the strength of the vector field becomes stronger because z is going larger. And when you're below the xy plane, then z is negative, meaning that the vector field is pointing downwards. So this will be the full diagram of that vector field. Okay. So this 1, 2, 3 are a demonstration of how you can draw a vector field on a coordinate plane or a 3D coordinate system. Okay. Basically that is what this section is saying. And now we're just going to demonstrate a bunch of examples to get kind of a connection between physics and math, and also some mathematical examples. So first of all, the well-known Newton's law of gravitation shows that the the force gained by the gravity is equal to minus gmm divided by x cubed x. So let's go through the notation one by one. First of all, this g is simply a constant. It is called a gravitational constant, given by this very small number. That is basically why you and me do not have that much gravitational force between each other. The second m here is the mass, with the unit being kilograms, of the object at the position 0, so at the origin. And this m here is the mass of the object at the point x. And then you see that we have a unit vector here, x divided by the magnitude of x. This is similar position of x, right? We care about the direction of the force. And negative sign here tells you that the force is actually attraction, meaning that the mass here, the capital M here, is actually attracting this little m here. So that is why you have a negation here, because you're not going outside x, but going inside minus x. Okay? So this is how the gravitational force works. And you can see that the magnitude, after taking the, I should put a double vertical line here. So the magnitude of the gravitational force is given by, you can see that if you take the magnitude of this x, it cancels out the denominator. So you simply get gmm divided by x magnitude squared, which is proportional to 1 over the magnitude squared. Which is kind of obvious because, not obvious, intuitive, because whenever you're far away from origin, then the attractional force should be lesser, right? And that is why you have this kind of phenomenon. When you're close to the object, you get stronger gravitational force. When you're away from the object, you get lower gravitational force, provided that both of you guys have the same mass. And as I mentioned, the direction is simply the attraction direction. So you have not x, but minus x, and we normalize it by the magnitude of x. So whenever you are, the gravitational force always attracts you to the origin, which is where the capital M, the mass, is. Okay, so this is one of the vector field. So you can draw it out, and it should be like this. When you're closer, you get a stronger vector field. When you're farther away, you get a less strong vector field, weaker vector field. The second example is a similar law. It is called a Coulomb's law. So Coulomb's law describes how electric charge generates force towards or towards each other. So in vacuum, we can describe the electrictional force, actually electricity, electricity, anyway, force generated by electricity charge by this formula. Y number 4 pi epsilon naught. So this is just a constant. You don't have to care about that. The epsilon naught here is called the vacuum permittivity, but we don't really care about that. It's just a constant. We have Q, capital Q here, to be the charge at the position of the origin. And a little q here is a charge of the object at the position x. And again, we have the unit vector x over x, and also the radius squared in the denominator. So we can see that the magnitude, taking absolute value, is always the constant times the absolute value of these two guys divided by this guy squared. Again, it is proportional to the inverse 2-degree squared, meaning that if you're farther away, then the force on you will be smaller. And why do I put the absolute value here? It's because that in this case, capital Q and Q might be negative. This is different from this guy because mass is always positive, but the charges has two different types, right? The negative charge and the positive charge. It depends on you're an electron or like a proton. So you see that whenever you have a positive charge and a positive charge, or a negative charge and a negative charge, then you have a repulsion. the direction of the electronic force is actually pushing you away from your position against the origin. And when you have different charges, a negative charge and a positive charge, then you have an attraction. So your charge is pulled to the origin. Okay. For example, in this case, I put the origin as a positive charge, and this is a negative charge. So you have an attraction here, and you have a repulsion here. Okay, a little bit different from the Newton's law because there is a different polar phenomena going on here. You have a positive charge and a negative charge. Okay, so those are the two classical physics example. We'll be coming back to them afterwards someday. Now let's do some mathematical examples. So in this case, we're introducing a very important kind of example, which is the gradient vector field. So gradient vector field is basically vector field generated by gradient of a function. For example, you see given a function, in this case a two-variable function of cosine x squared plus xy, you can take the gradient field, meaning that the first entry will be the partial differentiation of this guy respect to x, and the second entry is this guy differentiation respect to y. So this is a vector field, right? You see that we assign a point towards a vector. So a similar thing happens if you're dealing with a 3D function. Given a three-variable function, you can do the gradient, which again gives you a three-dimensional vector. You have partial x, partial y, and partial z. So this is called a vector field. In particular, we're emphasizing on this gradient vector field, which we will see why it is important afterwards. But for now, let us define this kind of vector field to be called conservative vector field. So to be precise, a vector field F defined on some, in this case, a two-dimensional domain. You can obviously extend it to three-dimensional. It is called conservative on the domain if there is some function so that the vector field is equal to the gradient of that function. Okay? In this case, this function F is called the potential of this vector field, capital F. So for example, this guy will be the potential of this vector field, and this guy will also be the potential of this vector field. Okay? Now, there's perhaps two remarks I want to make here. First of all, be careful with this kind of terminology. We're saying that it is conservative on omega. So it is conservative on a particular region. It can be conservative on, say, R squared, which is the whole thing, but it can also be conservative on only a small portion of the domain. It depends on the domain. I want to emphasize on that. The second problem is, does this definition actually make sense? Meaning that will all vector fields be conservative? If not, then how do we see whether it is a conservative vector field or not? So let us show an example. So given that this vector field fxy defined on a 2D plane given by 2x plus y x squared, I want to show that it's not conservative on R2. So suppose it is, let us write the capital F to be a potential, a gradient of a potential function, which means that the first vector field is some partial differentiation with respect to x, and the second one is a partial differentiation with respect to y. Now we see that again by Claire's theorem. So trace back your memories to I think section 14.2 or 3. We see that fxy is always equal to fyx, right? The differentiation order does not change. The second partial differentiation. So since fxy is equal to fyx, we know that this guy is the partial differentiation of fx with respect to y, right? And this guy is the partial differentiation of fy with respect to x. By our assumption, this guy should be him. So you have 2x plus y differentiated by y. And you have x squared differentiated by x, where you get 2x and 1 here. So that means that 1 should be equal to 2x, which is not possible, right? Actually, only at a point, which is x equals to half. But I claim that it is not conservative on the full plane, which is true. So because of this not valid equation, we know that the vector field must not be conservative. Because if it is, then we should have 2x equals to 1, which is not possible. Okay? And this is a small remark I made previously. So it might be non-conservative on a domain omega, but be conservative on a smaller domain omega prime belongs to omega. So the domain is actually important. We'll be emphasizing it afterwards. So whether a vector field is conservative actually has something to do with this domain. Okay, but anyway, you'll see that now we have provided a kind of criteria for analyzing a vector field is not a conservative vector field. So we are not yet sure how to verify conservative, but we know how to verify non-conservative. And that is the following theorem. So we see that if a vector field is conservative on a region omega, then we must have, in this case, I denote f by pq. So this is the x component, this is the y component. Then this being fx and this being fy tells you that we must have partial f partial y, partial p partial y equals to partial q partial x. Okay? Because the first guy, in this case, this will be simply partial square partial y. And so this guy. So if it is conservative, then you must have this equation. Similarly, for a three-dimensional vector field, if PQR is conservative, then PY and QX must be the same just as before, and also QZ and RY must be the same. Similarly, RX and PZ has to be the same. So this is kind of a necessary condition showing that a conservative vector field possesses this property. So for any vector field that does not have this property, for example, this vector field, then it must not be conservative. However, we are not sure whether this condition are sufficient. This is what I'm saying here. So we call usually the star and the star-star condition to be a closed vector field. This is another terminology for vector field. And for this theorem, we now know that via Claire's theorem, exact vector field, or say conservative vector field, I forgot to mention this, we also usually call this exact. This is a more mathematical terminology. But anyway, a conservative or exact vector field implies that you must be closed, meaning that if you are a gradient of some function, then that particular vector field, the components must satisfy this equation if you're in 2D and this if you're in 3D. However, it'll be a virtue, it'll be a very nice consequence if this actually implies that you can find such a potential function. So we're asking the question, does closeness imply exactness? Meaning that if a vector field demonstrated like this, PQ or PQR, if after I verify star or star star, then when can I conclude that you have a vector field F being conservative? And the answer is yes or no. It actually depends on whether what omega and E looks like. This is called Poincaré's theorem, and we'll be introduced this in section 16.3, which deal with more properties of conservative vector field and why it is important, right? Okay, so I'm very happy to start this journey on the vector field discussion. We'll be seeing a lot of fascinating things in this chapter, which sort of combines what we have learned in chapter 14 and chapter 15. So those are basically tools on differentiation and integration. And now we're going to see some theorem, some application of those two particular techniques combined together. Right. I will see you guys in the next video. See you.